think we'd get such a turnout for our safari today? It's like your grades depend on it or something. Anyway, my name's Safari Stu, and me and my team will be leading you on an exotic safari. We'll be traveling through the body and seeing what antigens and antibodies are and how they interact within the body. Well, look there. It's the first of my teammates, Know-It-All Nancy. She can be kind of a pain sometimes, but she knows her stuff. Introduce yourself, Nancy.
Hey guys, I'm your resident expert on antibodies and antigens, and well, pretty much a lot of stuff. As we go through the safari, I'll be letting you know some fun facts about them.
Can we get this started? I want to go home.
Guys, this is Babette. I don't know why she's on the team. She's Bob, but in a girl.
I'm here because I want to get paid, so let's get the show on the road.
Okay, let's go.
Wait, why do you guys always start without me? I'm Curious Kathy, and I ask the questions that matter.
Okay, so now that everyone is here, let's jump in the magic car. I would call it a bus, but apparently there are some copyright issues with that. First thing we need to do is get really small and disguise ourselves so the antibodies won't attack us.
Why do we need to do that?
Because if we don't disguise ourselves as something simple and known to the body, an immune response will occur. If we go in as something like a protein, which is more complex, stable, and bigger, we are more likely to cause a response. Whereas if we go disguised as a carbohydrate, which is smaller and less complex, we are less likely to induce a response. We should also go in disguised as something known to the body, because the more foreign an antigen is, the more likely an immune response is to occur.
So basically, to dumb it down, if a small child came into your house, you wouldn't attack it. But if a strange adult came into your house, you'd be more likely to defend your house.
Yep. Also, degradability is a factor in antigen provoking an immune response. If the antigen degrades rapidly, there's no time for an immune response to be elicited.
Okay, well let's go in as a glucose molecule then. It is definitely known to the body and it is a carbohydrate. To begin our safari, we're going to go in through the eye.
Wow, look at all those bacteria trying to get into the eye. What will stop them from getting in?
Good question. You see those Y-shaped things attaching to the bacteria? Those are IgA antibodies. Golly, our first antibody. This is so exciting. You see, the bacteria is seen as an antigen by the body, and IgA is an antibody that is found on the surface and in fluids like tears. That's how I know it's IgA, because it's in the tears.
But how does the IgA know the bacteria is an antigen, and how is it attaching to it?
Well, you see, on any antigen, there are structures that are recognized as foreign to the immune system. These structures are called epitopes, and they are where antibodies or T-cell receptors bind to the antigen.
Okay, but what about the antibody? What part attaches to the antigen?
The antibody has two parts. The FAB part, that is the top of the Y, and then the FC, which is the bottom part. The FAB is what attaches to the antigen, and it has two binding sites on it.
So basically, an easy way to remember it is, the fabulous part, the Fab, attaches to the epitope, and when they're bound together, it's called an immune complex.
Exactly. Also, the strength between the epitope and antibody binding site is called affinity. And since the FAB has two binding sites, it has more than one affinity, which is measured as avidity.
We are now in the bloodstream where the majority of the antibodies are. That's how technologists test your immunity to certain diseases like Hep B. They take your blood and dilute it, making titers, and introduce the antigen into the different levels of dilution. The last level, where there is agglutination, the forming of an antibody-antigen complex, is what your titer is, and based off what acceptable levels there are, they can determine your immunity.
But how are antibodies even made? They're just always floating in the system?
Well, antibodies are made by plasma cells, which used to be B lymphocytes. They can make more general antibodies like IgM, and more specific ones such as IgG. They are signaled to make antibodies by the T cells.
Okay, but how do they know to make general or specific antibodies?
I think we are about to see. This person has recently had their first immunization. Look, you can see deactivated Hep B virus used for immunization, and look at what's coming.
Is it snowing? Am I crazy? We're in the blood. How's it snowing? Those look like snowflakes.
They are actually IgM antibodies, much bigger than other antibodies, and they do have a snowflake-like appearance.
Since this is first exposure, the plasma cells make more IgM because it's generalized antibody. However, upon repeat exposure, the body can recognize the antigen, thanks to B memory cells, and produce specific IgG antibodies against the antigen.
So once the antigen-antibody complex is formed, does the antibody destroy the antigen?
No antibodies can destroy antigen by themselves. They can only inactivate them and opsonize them.
They can also activate the complement system.
And opsonization means what exactly?
Preparing them for dinner, it makes the antigens more appealing to the phagocytic cells.
Oh, cool.
Wow, look at that, it's a flu virus. Amazing, and look at all those IgG antibodies attaching onto it.
See, this was what I was saying earlier. This person must have been previously exposed to this strain of flu virus. Therefore, specific IgG antibodies were created as an immune response. IgG is actually the most prevalent of the antibodies, accounting for 70 to 75%. They are also able to cross the placenta barrier during pregnancy.
See how many of them are linked together? That can activate the complement system like I said earlier. However, it requires some IgG together to activate it, unlike with IgM where one antibody can activate the complement cascade.
So if you think about activating the cascade as a light switch, a tall person can just flip the switch, but shorter people have to sit on each other's shoulders to switch it on.
Yeah, exactly.
Here we are in the tissue. We only have one last antibody to see and then we are out of here.
And what antibody is that?
That would be IgE, the antibody that's most associated with hypersensitivity reactions and parasites.
That would be correct. How IgE works is that it binds to the surface of the mast cells and basophils to encourage degranulation of the cells. Then granules are histamine and heparin and are secreted out of the cell and do things like increase vasodilation so other cells have an easier time getting into the tissue.
IgE is related to hypersensitivity type 1 reactions.
So for example, it can be caused by allergens like pollen or wasp sting.
Yep, just like this guy here, I'm pretty sure he was stung by a bee.
Yeah, we should get out of here before the inflammation reaction gets too bad.
That safari was cool, and I learned a lot, and learned and saw a lot. I do have one last question though. Do all antigens come from sources outside of the body?
Nope.
What Babette meant to say was no. There are actually antigens found throughout our body, found on tissue surfaces and even on red blood cells. These antigens are called autoantigens.
And when our immune system is working properly, no antibodies try to attach to these antigens, but in some autoimmune disorders, our body makes autoantibodies against them because they don't recognize them as self-antigens.
Oh, interesting.
Okay guys, we are done. Safari happened. I'm peacing.
Well, thanks for coming on the safari, and I hope you learned something. Safari team over and out. To begin our safari, we are going to go in through the eye.
Wow.